Welcome back to The Explainer. Today, we're diving into a seriously high-stakes topic for all you engineers and designers out there. We're talking about how to size cable tray width and depth perfectly right before that specification gets permanently frozen. You know, this is one of those critical make-or-break engineering moments where a tiny oversight on paper can literally snowball into a massive, expensive logistical nightmare on the job site. So we're going to unpack exactly how to get this right, ensuring your designs translate flawlessly from the digital schematic to physical reality. Okay, picture this. It's a scenario that causes some real cognitive dissonance, right? You spend hours drafting, calculating, and validating every detail. Your spec runs up the flagpole, passes the rigorous chain of command, it gets stamped, it gets approved, but then, weeks or months later, it completely fails during the actual installation. What gives? I mean, the math was theoretically right, the software didn't flag a single error, but the physical install still hits a brick wall. This crazy disconnect between a past review and a failed physical install is exactly what we're going to solve today. Okay, let's dive into this. Here is our roadmap. First, the specification trap. Second, width versus depth explained. Third, the 5-step sizing workflow. Fourth, hidden mass and load classes. And finally, standards and compliance. Section 1, the specification trap, passing review versus failing installation. There is this super dangerous assumption just lurking in drafting rooms everywhere. This idea that width and depth are somehow interchangeable decisions, or, that if you solve for one, you've essentially solved for the other. Guys, this is a massive trap, and this quote hits the nail on the head. Getting one right without checking the other is how a specification passes review and fails installation. It is so true. You might have absolutely nailed the width perfectly to accommodate your cable count, but if you neglected to rigorously check the depth, your approved spec is basically a ticking time bomb, just waiting to go off on the construction site. Moving on to Section 2, width versus depth explained, dismantling the assumption. And this brilliantly illustrates why we have to clearly separate the physical responsibilities of these two dimensions. They simply do not do the same job, and they definitely can't be treated as an afterthought. Look at the left side here. Width governs fill capacity, literally how many cables you can physically lay side by side, and it heavily influences the bending load of the tray. Simple enough. But now look at the right side. Depth is an entirely separate beast. Depth dictates your cable layering, it governs the structural stiffness of the side rails, which is absolutely crucial for preventing sag, and critically, depth governs ventilation. If your tray is too deep and packed tight, that heat has nowhere to go. Width and depth handle entirely separate physical behaviors, which is exactly why they literally cannot be sized independently. Now, this whole thing gets even more complex when we start mixing in different standard tray varieties. Because even if you lock in the exact same nominal width, the structural behavior and the rules completely change depending on which of these standard tray families you're actually using. Whether it's ladder trays, perforated trays, or solid bottom trays, they all interact with width and depth differently. Seriously, a 600mm wide ladder tray doesn't manage load, stiffness, or airflow the exact same way a 600mm wide solid bottom tray does. You've got to account for what changes between these types, even when the width looks the exact same on paper. All right, Section 3, the 5-step sizing workflow, the practical solution. So let's shift gears from the cautionary tales to the empowering stuff, the practical sizing framework you actually need to use to guarantee success. Think of this as your bulletproof workflow. But the absolute key here, you have to follow these steps in exact order. Step 1, it all starts with your comprehensive cable list. Step 2, from that list, you determine your required fill capacity, which is going to heavily dictate your width. Step 3, and actually, this is the one people always skip. You assess your layering and your required stiffness, and that locks in your depth. Step 4, only now do you go ahead and pick your standard tray size based on both of those isolated calculations. And finally, Step 5, span verification, making sure the whole system holds up structurally over the required distance. If you follow this to a T, from the initial list to the final span, you completely eliminate that specification trap. This brings us to Section 4, hidden mass and load classes, the gotcha variable. Now, what's really interesting about this slide is that even if you follow that 5-step workflow flawlessly, based on your cables and tray dimensions, there are these surprise variables that catch even the most seasoned spec writers completely off guard. Notice this massive figure, 15 to 25%. That is a massive amount of hidden mass per meter that often goes completely unaccounted for in those initial digital models. Just imagine finalizing your specs, thinking your load is perfectly balanced, and suddenly out on the site, your physical installation is a quarter heavier per meter than you actually calculated. No way, right? So where exactly is this 15 to 25% coming from? Well, the culprits for all this hidden mass are the essential accessories. We're talking covers, protecting the cables, barriers separating your different voltages, and the splice plates holding the whole shebang together. And the result of ignoring these? That extra mass can fundamentally change the load class of your entire system. A system that you designed for a medium load class might suddenly cross the threshold into a heavy-duty requirement, simply because nobody factored the covers and splice plates into the mass per meter. It's a real game changer. Section 5, Standards and Compliance, Grounding the Framework in Reality.
Look, it's one thing to understand the physics of width, depth, and hidden mass in theory, but we need to anchor this five-step framework into real-world international compliance. And this is where Xinma, or Shanghai, Xinma, Busway, and Cable Tray Co. Limited, really comes into the picture. They manufacture these comprehensive product solutions, including cable tray systems, busways, seismic bracing, and intelligent cable management. And they're operating in some incredibly high-demand, zero-tolerance markets: data centers, rail transit, industrial plants, and commercial buildings. You simply cannot survive in these environments by guessing depth or ignoring hidden mass. You survive by strictly adhering to critical international compliance standards, which Xinma does. They specifically align with IEC 61537, NEMA VE 1, BSEN 5085, and GB 31251. These standards exist for a reason, right? To ensure that fill capacity, stiffness, and load classes are mathematically proven, not just assumed.
So I want to leave you with a final, somewhat provocative thought for the day. Go back to your desk today. Take a hard look at your pending specifications, the ones waiting for review or even the ones that just got stamped. Did you truly size both the width for fill and the depth for stiffness and ventilation? Did you actually calculate the hidden mass of your splice plates and covers? Or did you kind of just guess one variable to satisfy the other? Try using this framework, isolate those dimensions, and never let an approved spec fail on your watch again. Thanks so much for joining me on this explainer, and I'll catch you next time.